11:30, we're going to start today. So last class we showed that we had this funny definition of the tilde equals, right? And the tilde equals was how we were defining the space L1 of R, and L1 of R is functions that you make by doing them tilde equal to a bunch of step functions. So L1 of R, it was the set of integrable functions, and it was f such that you can find there are step functions. There are step functions, such that f equals, with a tilde, f1 plus f2 plus dot dot dot. And this little tilde equals, right, this really weirdo tilde equals is doing all the defining in this course. So for the Lebesgue integral. So it has the pointwise convergence, but only on the sort of the good set where things converge absolutely. And then also part of the definition is the f1s have to be absolutely summable in integral. So they're step functions, but they're step functions that their sum of their integrals in absolute value is actually very reasonable. Adds up to something finite, even though there's finitely many of them. And things were working pretty well. So we had f, if f is in L1, we said the absolute value of f is also in L1. That was what we proved last class. And we have most of the things we need. But now we're going to ask an interesting question. And it's directly copied from the textbook. So in the construction described in the preceding sections, that's what we've been doing the last couple of days, we start with an integral defined for step functions. So we started with base times height for step functions, and we extended it to a larger class of functions by expanding them? Ooh, that's a fun typo. I think they wanted expanding. Expanding them in a series. Is this like some English phrase? Have you ever heard of expending a sequence of functions? I don't know. Okay, anyway, expanding them in a series of step functions. F tilde equal, right? Sim equal f1 plus f2 plus f. Okay, that's what we did so far. Here's the question. Are we going to obtain new functions if we repeat the construction and use integrable functions instead of step functions? Let me go down here and draw a little analogy. So we had f, which was some arbitrary function, and we wrote it in terms of step functions. And I'm going to write step over here so you remember. So f was f1 plus f2 plus dot 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 for step functions, and we got L1. So L1 was defined like this. L1. Okay, and now you could ask, what would happen? What if we do f, and we write it as a sum of L1 functions, L1. So we write f1, which is in L1, L1, plus f2, which is in L1, plus f3, which is in L1, dot, dot, dot. And we copy the same tilde equals definition. In fact, this tilde equals definition is going to be definition 2.5.1. It is identical word-for-word copy of the previous definition. The only difference is the ingredients, instead of being subfunctions, they are integrable functions. So the f's you get, they are L1 functions over here. But other than that, it's like exactly the same. So it's like you have kind of thinking of taking like your Lego bricks and building something bigger. Originally, our Lego bricks were step functions, we built something out of them. And now we're like, what if we take the things we built and we do it again? We built something out of them. And there's two possibilities. Either we get something like cool, we get some like new exotic space. So what could happen? What could happen? We could get like L1 super or something, like some super space, some like crazy space that includes all the L1 functions, but new functions that were not in L1. Or maybe you just get L1 again. Okay, and this is a common kind of theme in math. I'll give you an analogy. The same kind of thing happens in algebra class. Apologies to those who don't like algebra. If you have the real numbers, and then you look at polynomials with the real numbers. So you look at the polynomial, x squared minus 4 equals 0, and the polynomial x squared plus 1 equals 0. Some polynomials have real roots. So we're in the real numbers. We made polynomials with the real numbers. And x squared minus 4, totally legit polynomial. It's got roots 2 and minus 2. We're very happy. But the polynomial, x squared plus 1, even though all the coefficients were real, has no real roots. And then we're like, okay, what if we chuck in, we're gonna make a new number. Real numbers are not cool enough for us. We're gonna make even cooler numbers. C stands for cool numbers. Okay? And the cool numbers are the real numbers plus the roots of all the polynomials you can make with real numbers. And it turns out the only thing you have to add is I. So C is somehow R plus I times R. Most people call them the complex numbers, but the cool numbers would be a way better name. I guess that would imply the real numbers are uncool. Maybe that's not allowed. Okay, anyway. So it turns out if you just chuck in this x squared plus 1, you get the imaginary number I. If you add the number I to the real numbers in the right way, then you get the complex numbers. And then you can say, okay, now I can make all sorts of other polynomials. Like what about the polynomial x squared plus I equals 0? You see, this is a polynomial in the complex numbered world. And then you can say, okay, now you make new polynomials. Where are the roots of these polynomials? These are the polynomials you can make with coefficients from C. What about the roots of these polynomials? And it turns out that when you do this, spoiler alert, no new, all polynomials in C. So even if in the real numbers there was polynomials that didn't have roots in the real numbers, in the complex numbers, all polynomials in C, so by that I mean with coefficients in C, have roots in C, Some people call this the fundamental theorem of algebra. The fundamental theorem of algebra. I remember this because in my first year algebra class, they made us memorize the proof of the fundamental theorem of algebra. I cannot tell you anything about that proof except for that I definitely 100% knew it cold for the final exam. That's the only thing I remember. Okay, so when you extend the real numbers to the complex numbers, and you try to do it again, you don't need to do it again. You've already gotten everything. So people call this, they say C is complete. C is algebraically complete. Algebraically complete. Okay, and we got the same kind of story over here in our class, where we started with step functions whose integrals we knew, and then we said we build them up, we build up sequences of step functions in this funny way, and then we get the L1 functions, and now we're doing it again. And the question is, do you get something new, or do you get the same thing again? If you get the same thing again, then you would say that L1 is complete. And remember, we had complete earlier in the course, and it's going to turn out that really this is saying that L1 is complete. And this is like analytically complete. It contains its limits. And that is going to come up later, because the answer is, spoiler, as they say in the textbook right here, it turns out that we do not get anything new, which is such a boring way of putting it. I think it's more exciting to say L1 is complete, so it contains all its limits. I think it's a positive statement that we don't get anything new. That means we can stop after this. We don't have to just keep going forever and ever and ever. Okay, so that's the sort of the big idea. Questions or comments about any of this stuff? Who's heard of the fundamental theorem of algebra before? Okay, great. Fantastic. Okay, questions or comments? Yeah?
Is the reason why it's just the same thing is because it's so f would be if it's the sum of step functions, the sum of countably infinite step functions.
Yeah.
And then if you sum up a countable number of countably infinite a countable number of integral functions is still countably infinite.
Yes, this is a fantastic way of thinking about it. So each f being an L1, each f is by itself a countable sum of step functions, and so you have a countable sum of a countable sum. Actually, let's write this down. This is a really good thing. So this is the idea of why it's probably true, and you're going to see there's one obstruction. So let's write f, which is we'll write it as in an L1 sum of f1 plus f2 plus f3 plus ... So f1, f2, f3 themselves are L1 functions, not step functions. But now each fi can be written as its own thing. So let's write it like this. So f1 can be written as step functions g. Okay, now I need two notations. So I'm going to put the 1 upstairs, and I'll do it like this. g2 1 plus g3 1 plus ... And f2 is the sum of step functions of g2 1 plus g. Oh no, I have. You must pretend I didn't make the embarrassing mistake. Okay. 1 2 3. I want it like that. Okay, 2 g2 3 plus ... And let's do one more for good measure on the board. Step g3 1 g3 2 plus g3 3 plus ... Okay. So in other words, f is made of L1 functions, and each L1 function is made of step functions. And so what I can do is I can show you that the function f you want is actually also made up of step functions by counting up all the step functions g, and then showing that they add up to f in the L1 sense. And to count them up, this is the kind of argument with countable that you hopefully have seen before, where you make a big snake. So you go like this and make a big snake. So you snake all the g's, and there's going to be a countable number of g's. And if I go through them in order, so I write f is g11 plus g12 plus g21 plus g31 plus g22 and so on. So I count them up. Then we have a candidate for what f will be. So this is a great idea. Unfortunately, this as written will not work. You need to ensure something is nice, and that's going to be the first limit, is ensuring the nice thing. Does anyone have an idea of where this could potentially go wrong? Yeah.
Like each f has a certain set of x's that the bad set.
Yes.
The bad set is different.
That is okay. That is a fantastic point. Is the bad set for each of the f's could be different. That is one thing you would have to worry about. But it turns out the sort of the bad sets are okay with countable things as well. So even though each f individually will have a bad set, the countable union of all the bad sets will be still a fine bad set for f. So this is one possible concern, but that will take care of itself. Yeah. So this is a good thing to keep your eye on. Anyone else have an idea of something? What could go wrong in this kind of approximation? Okay, it's kind of a subtle thing, which is it has to do with sort of where the errors are. So as I've written it, f is equal to this infinite limit of the g's, and there's some amount of error. So like if you give me an epsilon, I need to go some depth into the sequence of g's to make sure that it works. And f2 will have some other amount you have to go into, and f3 will have some other amount you have to go into. So for one fixed epsilon, there's sort of an amount you have to go into each sequence to make sure that the error is less than epsilon. And the problem is the error as we go down could be getting worse and worse and worse. So it could be that you need sort of 10, let's say, let's fix epsilon. So for fixed epsilon, so you're going to have an n1, an n2, and an n3, which is how far you need to go into the sequence to make sure that the error between f3 and the sum of the g3s is less than epsilon. And the problem is the n's could be getting worse and worse and worse and worse. So it could be that, for a fixed epsilon, you only need like 10 terms for f1, you need like 20 terms for f2, but then it gets more and more and more and more. And then the problem is your snake sort of won't visit. If the n's are getting bigger, then your snake is getting bigger. Like if the n's grow faster than, I guess, quadratically here, then your snake will sort of never reach the zone where things go. So in other words, there's sort of like a good zone of where things happen, which is like after n1, after n2, after n3 in this grid. And if that grows too quickly, then your snake will never make it into the zone where the errors are small. So we have to control this problem. We have to make sure that this situation doesn't happen. We need some kind of way to control how big the error is. And so it's not enough to start with any sequence of g's. We're going to start off with a specific sequence of g's where we can control the error. And when we control the error, then the snake thing will work perfectly fine. So in other words, we're going to cook up a sequence of g's so that we know exactly how big these n1s are. Yeah, that's going to be the idea. That's actually the whole big class today. The big theorem from the class today is exactly doing this kind of thing. Okay, fantastic. That's our idea phase for today. Yeah.
I'm kind of lost on exactly what the n's mean. Is the n like for each 1, 2, 3, and so on? The n is the number of terms. The
Yeah.
number of g's you need to exactly approximate.
Yeah, to approximate f1 in terms of epsilon. So let me write down. So it depends on epsilon. So n1 is the number of g's such that, let's write it informally, number of g's such that f1 minus the sum of the finite sum, I equals 1 to n1, of g1i is less than epsilon.
Oh.
And formally, it would be something like, the thing you actually would care about is the sum starting from n1 plus 1 to infinity of, say, the integral of the absolute value of gi. That should be less than epsilon, right? And this is the kind of control we were doing yesterday. If you know the sum of the integrals is less than epsilon, then this kind of approximation will be good to up to epsilon. And so that's exactly, that's what I mean. So it's like how many you need to go until you have approximated f1 to within an error of epsilon. Yeah. And so this is an issue that comes up a lot in these kinds of grid things. It's like a race of like, is the error getting bigger than we are reaching the terms? And sometimes if you win the race, then it's good, it's all fine. And if you lose the race, it can go bad. And then you get these like weird statements that the limits aren't what you think. Okay. This is some kind of issue about pointwise versus convergence in Norm, we had the same kind of picture when we were doing things with like sequences of sequences, right? Same kind of issue. Yeah, fantastic question. And that is what I meant. Okay. Other questions or comments? Okay, so the first lemma we're going to do is telling us that not only can you find for every f in L1, like this f1, not only can you write it as a sequence of step functions, you can write it as a sequence of step functions, and you can control how big the error is. Okay, and that is a lemma from the book. Let me give you the number of the lemma. So this is lemma 2.5.2. 2.5.2, and sort of in words, what it does is create a sequence of step functions with control on how quickly the error gets bigger. Okay, and so what it says is if f is in L1, so we know that we can write f as a sequence of step functions, but there's a special way you can do it. And for any epsilon greater than 0, there exists a special sequence of step functions that depends on epsilon. The textbook obviously doesn't write special, but I will write special. Special sequence of step functions depending on epsilon such that the following is true. And the thing we are controlling is the integral of the absolute value of f. And we're going to compare that to the sum of the absolute values of the fi's. Let's call these fi's. Fi. And we saw last class that it's always less than the sum of the integrals. So this will happen no matter what in the definition. I equals 1 to infinity. Let's do n equals 1 to infinity. And it's the integral of fn. Okay, I guess I want, the sequence I'm talking about is going to be a tilde equal sequence. So f is the sum of the fn's, and we're going to control the thing. So this is always true. We saw this last class. It's always true this way. So this one's not even in the lemma. This is in a previous lemma. But the thing that is new in this lemma is the other side of the inequality, which is this lemma. And this is the special sequence, is not only is the absolute value of upper bounded by this, but it's almost lower bounded by this up to an error of size epsilon. So you do the sum of n equals 1 to infinity, same exact sum as before of the integral of the fn, but now you subtract epsilon. So in other words, if you give me epsilon, I can find a sequence that sandwiches the absolute value of f within an error of epsilon. The absolute value of f in integral will be somewhere between the infinite sum and the infinite sum minus epsilon. We can control it really well. And by doing this, essentially, by doing the right epsilons, we're going to control this picture over here that we drew over there. That'll be the next theorem that uses this lemma. Okay, that's the statement. Is the statement clear? Yeah.
Are the FIs and the FNs different things? Or
No, they're the same. Yeah, I just mean the collection of all of them. So yeah, let me write fn over here. Some functions fn, and then I want n going from 1 to infinity. Right, so it's like the collection of all the f's. F is the special sum of all the f's, and also it bounds this way. Yeah. Okay. Okay, here is the proof, and the proof is actually kind of a, once you see the proof, you're like, oh yeah, obviously that's not so bad. And what we're going to start with f written in terms of step functions with some g's, g1 plus g2 plus g3. So since f is in L1, we can always find some step functions that work. We're calling them g's, so we don't get them mixed up with the f's from the statement. Plus dot, dot, dot. Then this goes on for a long time. You know, g, let's say 1,000, and then dot, 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 it goes on forever. And I'm writing g 1,000 over here. Let's write g 1,001 as well. I think I want 2 of them to illustrate this idea. So f is a big sum of step functions. But of course, you can, even just given this, there's a lot of ways you could rewrite the same sum. So for example, you could take g1 to g1000, and you could call f1, you could call that the sum of g1 plus dot 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 plus g1000. And the thing is, step functions are closed under finite sums. So f is the infinite sum of all the g's, but the sum of the first 1,000, you just call that f1, and then you can call like this one, call that one f2, and then, and so on, right? So if you call the sum of the first 1,000 f1, and that one's f2, and then the next one's f3, then f will be the infinite sum of the f's as well. So you can just like reorganize the sum in a lot of different ways. As long as you only ever do finite pieces, it's totally fine. And that's all you got to do. You just got to do this kind of rearrangement. Don't do it at 1,000. When someone gives you an epsilon, do it at the right number so that the tail is less than epsilon. Yeah.
So it's kind of like refining a partition.
It's a bit like refining a partition. And indeed, like if you think about what's going on in terms of pictures, like we had that class where we were writing y equals x as a sum of squares, what it's saying is make the first step function that you do approximate the whole function up to an error of epsilon. And that step function might be crazy complicated, right? It might have lots of like little tiny steps. But it's still a step function. It's a step function with 1,000 parts. It's still a step function. So as long as you make your first step function detailed enough, it will be close to the final function you want. And of course, you still need infinitely many other like microscopically small pieces to finish off f, but those things will be no more than size epsilon, and so this will be true. Yeah, exactly right. Okay, great question. Anyone else? Okay, so that's the idea, is we're going to do something like that. Let's erase this blue. This is some idea time. So formally what we're going to be doing is we're going to say, given any epsilon greater than 0, find n naught such that what? The sum from k equals n naught plus 1 to infinity of the integral of the absolute value of the gk's is less than epsilon. Okay, and I'm just going to check here. Do we want epsilon or do we want epsilon by 2? We want epsilon by 2. Okay, so the sum of everything past a certain amount is less than epsilon by 2. And then I'm going to define my f's now. Let f1 equal the sum of the first n naught things. g1 plus g2 plus this all the way up to n naught. And again, n naught might be some huge number, but it's a finite number. f1 is a finite sum of step functions. It is still a step function. And fn equals gn naught plus n minus 1 for n greater than or equal to 2. So f1 is sort of the first huge number, and then after that we just go one by one, and we know things are going to work out quite nicely. Okay, so, I like this. This is a good textbook quote. Let me screenshot this from the textbook for your amusement. Obviously, f is the same as f1 plus f2 plus dot, dot, dot. That is the thing we just said, right? So you can reorganize things with finite sums, and it's all still good. Yeah, in this case, it's really not complicated, but I think it's funny that the textbook says, oh, it's just obvious. Okay, so now we're going to use the triangle inequality by the triangle inequality, and we're going to do it like this. Yeah, let me do it the slow way. So the integral of f1 is equal to the integral of f1 plus f minus f. I think maybe I want minus f plus f for a little added thing. So this is a common trick with the triangle inequality, and this is less than the integral of f1 minus f plus the integral of f. Okay, so that's triangle inequality applied to these integrals. And therefore, if you rearrange it, you get that the integral of f1 minus the integral of f is less than the integral of f minus f1, or f1 minus f, I guess it's the same. Some people call this thing the reverse triangle inequality. I can never remember the reverse triangle inequality, so I always do the ordinary triangle inequality, I add and subtract the same thing, and then I break it up. That's how I always do it, and then I reverse it if I needed to. Okay. Okay, and then now we're going to have a big sequence of inequalities in a second here that are going to add up to less than epsilon. Okay. Okay, now we're going to say, we're going to look at this guy, f1 minus f. That's the same thing as the integral of f minus f1. And what is f minus f1? Well, f minus f1 is everything else. So this is equal to f2 plus f3 plus dot, dot, dot. I believe this was an exercise of life. If you have one step function, you can move it to the other side, and it's okay. So this is, again, we're just, f was everything, and then you move the f1 to the other side. It's all good. Okay, so f is like that. And therefore, what can we say about its integral? Okay, and therefore, the integral of f minus f1 is less than or equal to this infinite sum, and equals 2 to infinity of the integral of fn. This was the thing we proved last class. So those were the inequalities with absolute values, that if you can write something as an infinite sum, then its L1 norm is less than the sum of the pieces on the other side. Okay. Okay. And therefore, if we look at this thing, so if we combine this with what we had before, we have the integral of f1 minus the integral of f is less than or equal to this integral, f minus f1, and that is less than this big infinite sum. Okie dokie. I mean, this big infinite sum is the thing that is going to be less than epsilon in a second, but they just keep writing it out like this. So we're going to do the same thing. So what they do is they now move this over to the other side, and they say, therefore, the integral of f1 minus the big infinite sum, n equals 2 to infinity of the integral of fn, is less than the integral of f. Okay? Remember, what we're shooting for is that the integral of f is greater than the integral of f1, the infinite sum with the minus epsilon. We'll see that in a second. Okay. Questions or comments so far? So far, it's a big soup of inequalities. Yeah?
Never mind.
Okay. Yeah, let me take a second here. Yeah, this is the kind of thing where I think it's not, when you read somebody else's, you're always like, what the hell is going on here? And you kind of just have to sit and you're like, if I was trying to prove what they were doing, what would I do? And then if you think about it, you'll come up with the same sequence of inequalities. Like, so what they wanted to do is they wanted to get the integral of f, and the integral of f is almost the integral of f1, but it could be like a little bit smaller, right? And how much smaller could it be? Well, you can subtract off the integral of all the other ones. And so they did it like this conclusion is kind of like, makes sense. If f is almost the same as f1, then the integral of f will just be a little bit bigger than the integral of f1. And how much bigger can it be? Well, you can subtract off this amount. So it's kind of logical, and like this like soup of inequalities to get to here is like the thing you got to do with triangle inequality to get this thing that intuitively, I don't know, makes, if you just describe this, I'm like, yeah, okay, that makes sense. All right. Okay. Okay, let's continue. So now we're going to do a big sequence of inequalities. Remember, this thing is no more than epsilon by 2, so I'm just going to add and subtract it back, I think, to make this thing work. So okay, yeah, they do this kind of in the reverse. I'm just going to do it the way the textbook does it. The textbook, they have it nicely set up in the logical way with the absolute value of f on the other side, but then they write it, in the next thing, they write it the other way, which is fine. But so they start with n equals 1 to infinity of the integral of fn, and then they say that's the integral of f1 plus everything else, n equals 2 to infinity of fn. Okay, and then this is equal to the integral of f1 minus the sum, n equals 2 to infinity of the integral of fn, plus twice the infinite sum. Okay, and the whole point is to make this thing appear that we had from an inequality. Let's call our inequality heart. Heart. Okay, and then therefore by heart, this is less than or equal to the integral of f plus twice the integral, this infinite sum. And this thing, by the choice of epsilon and the choice of n naught, by choice of n naught, and that defined, and the definition of f2, f3, dot, dot, dot. So this is starting at 2 for the fn's, but in the g's, that's starting at n naught plus 1. This is less than epsilon. Integral of f plus 2, and then you have epsilon divided by 2 equals the integral of f plus epsilon. And that is what we wanted to show. This thing is no more than f plus epsilon. You move the epsilon to the other side, that will be the inequality that I saved. Okay, so I'm going to just leave it at that. Okay. So again, the main idea is just relabel the sum. So instead of doing the thing you're given, do it with the thing. Group together the first like 1,000 terms so that the error of everything else is no more than epsilon over 2, and then this sum will work out to be no more than epsilon of the integral of f. Okay. Questions or comments? Okay, now we're ready for theorem 2.5.3, which is the completeness kind of result that we mentioned before. Theorem 2.5.3. So if f is made of L1 functions, so f1 plus f2 plus dot dot dot, so fn are in L1 of R, they're not step functions, and you make a new function f out of the L1 functions you were given, then f is in L1 itself, so i.e. it can be written as step functions. Step functions. And not only that, the integral of f is the infinite sum of the integrals of the pieces. Right? So this was how we define the integral. We said if they're step functions, this was how we define the integral of f. But now we have the integral of all these things, of the f's, because they're in L1. And if you do the infinite sum of them, you get the integral of f. So this is kind of telling us that the space L1 is sort of complete. If you make things out of L1 functions, you're still in L1. L1 has all of the puzzle pieces needed. If you construct something from it, it's still L1. Okay. Okay, and the proof is exactly the kind of like picture we had before, but you don't just pick any arbitrary sequence of step functions. You pick step functions where you get to control the epsilon by the lemma we just proved. Okay, so we're gonna set epsilon equal 1 over 2 to the n in lemma 2.5.2. So maybe I should say for each n. For each n, so you give me n, I make epsilon equal 1 over 2 to the n in lemma 2.5.2. So I make it 2 to the n? Okay, I guess 2 to the n. I thought I would have to make it epsilon over 2 to the n, but I guess it's fine. Okay, we make it 1 over 2 to the n, and find a sequence of step functions, approximating okay, I'm gonna say approx because I'm out of room. Let's do that so I know my boundaries a little better. Approx, so fn is going to be equal to these step functions, and we'll label it the same way as before. So I'll put the subscript up here, fn, fn2, fn3, plus dot dot dot. So these are the step functions that approximate fn. I think I called them g's originally. Well, you guys like g's or you like f's? Let's have a little vote. Who wants to call it f? Who wants to call it g? Who could literally for any epsilon greater than 0 could not care less than epsilon? Okay, yeah. All right, let's just leave it f because I have f on the board. Okay. All right, yeah. So this is good, and I want the integral of the absolute value of fn to be greater. Let's write it in order. The sum from k equals 1 to infinity of the integral of fkn is less than, let's say, minus epsilon, and epsilon here is 1 over 2 to the n, so this is the epsilon, equals epsilon. This is less than the integral of the fn. So in other words, fn is approximated to within a 1 over 2 to the n error by this specific sequence we chose. And this is absolutely crucial, is that now when we do our big snake, because we know that the error is no more than 1 over 2 to the n, our big snake will make an error that is no more than some sum of 1 over 2 to the n. And 1 over 2 to the n is a summable sequence. So our total error is going to be arbitrarily, we can make it arbitrarily small. Okay, so that's the idea. Okay. Okay, here's another fun screenshot from the textbook. Okay, so the textbook called it G, but we called it F. Let Hn be a sequence arranged from all the functions g and k. So they're counting on you sort of like knowing all the countable stuff. But for us, let's really write it out. And what they're saying is put them in a big grid. So you put F1, plus F1, plus F1, 3, plus dot, dot, dot. And then over here is F2, 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 3. Let me not put pluses yet because we want to add them up in a sort of a different order. Okay, so this is the F1 approximation. F sub 1. This is F sub 2, and F sub 3 will be here. F1, 3, F2, 3, F3, 3, and so on. Okay, and we're gonna snake these in some kind of order. And so you can do any order you want. There are many possible answers, but the classical one is to go like this. Okay, and so we're gonna call this sequence, we're gonna call this H to match the textbook. So this one is H1 is that guy, H2 is this guy, H3 is this guy, H4 is that guy, and so on, H5, H6. So we're recounting this infinite grid, and we're doing it in a way that shows that it's a countable thing. This snake eventually hits every single number. Nobody is missed. Everybody is hit eventually after a finite amount of time. So it's important you do it in this way. You can't, for example, you can't do the first row first, because you'll never finish. But you can do this snake and get everybody. So that's the sequence H. So let Hn be a arrangement of all the F and Ks as above. Okay, and now things are going to be okay. So the integral of F, so F is sim equal to H1 plus H2 plus dot dot dot. And the reason this is true is the H's eventually get everything. So the limit, so for any, so I guess there's some stuff to check. Okay, here are the things you would have to check. So 1, is the limit as n goes to infinity of the sum of the Hn of x. What is that? Well, if you do the infinite sum of the Hns, that is the same thing as the limit as n goes to infinity. And it's the sum, you could do something like this. The sum of f and k of x, and you could sum from k equals 1 to n, and then you could sum from m equals 1 to n. No, well, this one goes from 1 to m, this one goes from 1 to n, and then you could check that these things are getting closer and closer to the f's. So this is the kind of like limit kind of stuff you would have to do. So this was the stuff you have to check if you want to be super crystal careful, but this is going to be the limit of the infinite sum of the f's. Okay, let's say n goes to infinity, m equals 1 to n of fn of x, right? So in other words, the h's, they catch everything, and so you can rewrite it like this, and then these things are getting closer and closer to the fn's, and so the limit of this stuff will be the same as the limit of this stuff, and that is f. So this is the kind of thing you would have to check. If you wanted to do it really carefully, you would have to make epsilon equal 1 over 2 to the n and do these kinds of things. Yeah?
On the left-hand side, the limit there, shouldn't it have a capital N at the top and we're limiting capital N as it gets bigger?
Oh, this one?
No, on the left-hand side, the first.
Ah, yes, very good. Okay, yeah.
Or whatever letter.
Yes, I have the letters wrong. Yeah. Yeah, I got excited. I wrote the infinite out 2 ways, and that's not right. Okay, yeah, thank you. Yeah, that's right. So this is the kind of stuff you have to check. This limit works. And where does it work? This works for every x such that, and you would like the these sums to be finite for all the things, such that the sum from k equals 1 to infinity of fkn of x in absolute value, no integral, f of x less than infinity, and you would like this to be true for all n. And when it's true for all n, then everything is good. So this is the sort of the set where it works. This set is the infinite union. You could write this as the union from n equals 1 to infinity of the set for each individual x. Okay, and this is the kind of thing we'll be doing coming up, is this is a null set, it's very small. This is a countable union of null sets, it's still gonna be a null set. Everything will still be okay, this set will work. And when this happens, all these limits are totally legit. So this is the kind of thing you would have to check for the limit, and then you would have to check that these things are finite. So this is like condition B, and then condition A is something like check that the infinite sum of the integral of Hn n going from 1 to infinity is finite too. And again, you write the hns. This infinite sum is actually the same as the infinite sum of the other ones. And because the, yeah, okay, let me write this down. This will hold because we are given that the sum from n equals 1 to infinity of the integral of the fn's is finite, is given. So this integral is essentially going to be a rewriting of all the fnk's, and each fnk bounds this guy, and then this thing will be finite too. So again, if you want to do it sort of properly, you would have to check all these things. The textbook just writes it down and says, that's it. Okay, yeah, so here's the screenshot of all the justification they give for this in the textbook. And I have to click on this. Okay, that's what the textbook writes. That's it. Okay, so they're like, you check it or something. I don't know. I don't know if they were like, you check it, or if it's so obvious to them. But in any case, that's what the textbook writes. And so now we have f as the sum. And now we're going to find the integral of f. So first notice, therefore f is in L1, right? L1 is things that you can write as sums of step functions with the tilde equals. We just did that. The h's were the things made of the f's. And the integral of f is the sum of these integrals, h1 plus integral of h2 plus dot, 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 dot. Okay. And this is equal I might have skipped a step here. Okay, this is going to be equal to the integral of the f's. f1 plus the integral of f2 plus dot, 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 dot. And then this is the thing that we wanted. The thing that I skipped is actually this little proof. Let's go back here. So actually, let's do this one in detail. Because it will involve these absolute values. That's where the 1 over 2 to the n's come into play. So let's put a little star here, and let's check it. Star. Notice that. So if you do the integral of fn1 plus the integral of fn2 plus dot, 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 this is less than the integral of fn plus 1/2, 1 over 2 to the n. Okay. And therefore, the infinite sum of all the h's, k equals 1 to infinity, of the integral of all the h's, the hk's, that is this kind of infinite sum over everything. So this is the double infinite sum from k equals 1 to infinity and n going from 1 to infinity of the integral of f and k. And this will be the infinite sum of the fn's plus, and then there's this extra term, which is the infinite sum of 1 over 2 to the k. So you have this, because each one is approximated with a 1 over 2 to the n error, when you add up all of them, you have the sum of 1 over 2 to the k of the error, and that is less than infinity. So in other words, the choice of the 1 over 2 to the n was crucial to make sure that this integral added up to a finite number. If the errors were blowing up in a way, they were going to 0 in a way that's not summable, then it wouldn't work. So this is kind of crucial. Therefore, property A holds. Okay, so this is where the 1 over 2 to the n was used. So okay, in conclusion, if you do the rearrangement and you make sure the error is this 1 over 2 to the n error, then everything works out. And you could verify this kind of thing. This is the limits, and then you got to verify this kind of thing, and then you get it. Okay, yay, we did it. All right. Questions or comments about that one? Yeah, it's very short. It takes like a third of a page in the textbook. Yeah.
Can you just explain the star thing that you just?
Yes, the star thing. Okay, so the star thing, again, I think the best way to think about it is with this picture. Okay, so we need to, the h's are snaking through and doing everything. We need to do the sum of the absolute value of the integral of all the h's. Okay, so we're doing absolute value of this, integrate it, absolute value of this, integrate it, absolute value of this, integrate it, and so on. That is the same as doing the absolute value of all the f's, or all the fij's, do the absolute value, then integrate them. So in other words, you can do them along the snake, or you can just like do the whole big grid. You can get the same answer. And the important thing is that we know that the sum of the whole big grid is going to add up to a finite number, right? And the reason it's going to add up to a finite number is when you sum up the first row, you get the integral of f1 plus 1/2. And when you sum up the second row, you get the sum of f2 plus 1/4. And then when you sum up everything in the third row, you get the third f3 plus 1/8, and so on. So even though there's infinitely many things, when you add them up, you're going to get this infinite sequence of f's plus 1/2, 1/4, 1/8, and so on, and that's summable. And so the whole thing will add up to a finite number. So in other words, it's just like rearranging the sum and comparing it to this, the sum of the f's. That's how I would say it. It's kind of a visual. For me, it's very visual. And the way they write it in the textbook, it's like one line. And it's exactly, a lot of the stuff is hidden in these rearrangements. Right? So they're saying the sum of the h's, that's the sum along the big snake. That's the same as the sum along the grid. And the sum along the grid is compared to the sum along the left row, or the left column, plus the error. Yeah. Yeah, great question. Yeah.
So in this case, you're summing up like a half plus a fourth plus an eighth.
Yeah.
That just sums up to one. So
Yes.
You need like an extra epsilon.
No, because we only need the sum to be finite, right?
Okay.
So yeah, this is, you remember early in the proof, I was like, do we need 1/2 to the n? I thought we needed to do epsilon. And so if you wanted to approximate it, if you're like, I need an approximation, I need to know how far into the snake to go to get an approximation, then you would end up with like, how far into the tail do we need for the sum to be less than epsilon? But because of the way the conditions have been cooked up in the book, right, the sim equals, right, this little crazy symbol that we're using all the time, it just says, oh, the sum has to be finite, and then when we do proofs using this, then we do the tail. So it's just enough for the sum to be finite, and that's why this thing would work. And you'll notice, like, we didn't actually need 1/2 to the n, right? Just any summable sequence would have been fine. As long as you can approximate them in a way that the errors are summable, everything will work out. Yeah?
What happened between the middle piece
Yeah.
and the right piece where like you no longer care about the ends?
Yeah. So the thing that happened is we used the infinite sum from k equals 1 to infinity of integral of f k n equals the integral of f n plus 1/2 to the n. Okay, and when I say equals, less than. So this is the big infinite sum across like the two-dimensional grid. And when you sum them up row by row, the sum of this entire row is less than that thing plus 1/2 to the n. Here, I can draw it over here. Yeah, these are great. So the sum of this entire thing, all these sum up to this plus a 1/2 to the 1, and so on. So the sum of f11, f12, and so on, if you absolute value and integrate them, it's less than the absolute value of this and integrate this. That's how we chose the fn's. That should be right up here. Yeah, look, it's written over there.
Then how do we get rid of the ends instead of getting rid of the k's?
Well, what we end up with.
The superscript is 1/2 to the 1, which
Yeah,
is what you
that's
use
right.
as ends.
Yeah. Uh-huh.
But at the end of
Yeah.
the proof, they're k's.
Okay. I see. I understand your criticism. Okay, this is a style criticism. Let's relabel the k's to n's. Yeah. Okay, no, this is good. Over here, I used n for the pieces, and I used fk, right? I think what you're saying is it should be the other way around. Look, I did fn. This really should be fn. And then what you're pointing out is I changed conventions halfway through. So here, I was saying n in the top is what row you're in, and then k is how far over you are. And then over here, I switched to k is the other way around. So let's fix it. I think that's a nice clarity point. And again, of course, it's mathematically equivalent, but I think it actually makes a big difference for understanding. So let's fix it. So this really should be n. Thank you very much. Fn. And then this one should also be n. Yeah. 2 to the n, and this is 2 to the n. So same sum, but you're absolutely right. It should be indexed. It makes more sense to index it like that. Yeah. Very good. Okay, these are great. Anyone else? Okay, so the conclusion is if you add up things in L1, you're still in L1. And there's a little corollary here. and this is a useful kind of corollary. So if you have a sequence of functions, if f1, f2, dot, dot, dot is in L1, so you have some sequence of functions, and the sum of the integrals is finite. So in the previous thing, we were given sort of some function f and a sequence of things. In this one, we're just given the sequence of functions. And this is a kind of a more typical thing you'll find in the wild. Normally, you have a sequence of functions, you want to do something with them, rather than being given a final function. The conclusion is then there exists a function f such that f is equal to this L1 limit of f1 plus f2 plus dot, dot, dot. So in other words, if you have a sequence of functions, you can add them together in the way that is explained. And the proof is just dealing with this weirdo set. So let f of x equal, it's equal to the infinite sum of the fn's if the infinite sum is finite, and it's 0 otherwise. So you just have to define the function so that it's 0 whenever this infinite sum is infinite, and it's the finite sum when the finite sum is finite, and that will work. So then apply previous theorem to this f. And the conclusion is this function is in L1. So not only is there a function, but there's an L1 function that is made like this. So this is a useful way. If you're given a sequence of functions, you can add them up as long as they're absolutely summable. Okay, that was a quick one. Questions or comments about that one? Why is this useful? You might remember when we were doing, back in the days of yore, when we were doing Banach space stuff, when we just had arbitrary Banach spaces, you might remember that there was this definition for what does it mean for a normed vector space. A normed vector space is complete. All right, and when they are complete, they're called a Banach space. A Banach space. This is yes, this is the perfect moment for my favorite math joke of all time. What is, okay, remember this. If you forget this, the joke is not going to make any sense. What is normed, yellow, and complete? It's a Banach space. Okay? Yes, see, this is very funny if you know what a Banach space is. Okay, okay, so normed vector spaces are complete. And remember, we said it's complete if and only if every absolutely convergent sequence converges. Every absolutely convergent sequence converges. And the theorem we just proved is exactly this, right? So if you have a sequence in L1 and you do this sum of the integrals, that's a bit like the sum of the norms. So remember, in L1 of R, the norm we're looking at, the norm of f, is equal to the integral of the absolute value of f. And so the corollary really says if f1, f2, dot, 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 is absolutely summable in L1, absolutely summable in L1 means the sum of the norms is finite. And the sum of the norms is the sum of the integrals. Then the sum, the infinite sum, n equals 1 to infinity of fn, it converges in L1. Okay, and that is exactly what we proved. So this thing is going to prove, this essentially proves that Banach spaces, or that the L1 space is a Banach space. Okay, this is actually going to come up later in the textbook. So this, I think this is all the way in section 2.8 for some reason. So this, we will do this formally in 2.8. And the reason is, there's a problem. There's a problem. Everything is morally fine and morally makes sense, but there's a big problem. And the problem is, as written, everything we've done so far, the integral of f1, this thing, so I've been writing the norm of f, is not a norm, is not in big fat letters, not a true norm. A true norm. So if you do this stuff, everything makes sense. This kind of convergence thing, if you have a sum that is finite, then it does converge. Everything is fine, except for this stupid issue that the thing we wrote, the integral of f, is not a true norm. And the reason it's not a true norm is it doesn't satisfy one of the axioms. It does not satisfy one of the axioms. Okay. Let me give you guys like 5 minutes. You can flip through your notes. What are the axioms of a normed vector space? And which axiom does it not satisfy? So this norm, it does most of them, but it doesn't do one of them. I will let you think for several minutes, and then we will reconvene, because it's kind of funny when you think about it. And you're like, oh, of course. Okay, time is up. Does anyone have an idea which axiom does it not satisfy? Yes.
F can be 0 almost everywhere. It doesn't mean it's like it is the 0 function.
That's exactly right. So the one that it doesn't satisfy is this one with 0. So remember, the norm of f being 0 is supposed to imply that f is the 0 function or the 0 vector. And that doesn't work for us. So the 0 vector in the space L1 is the 0 function, which is 0 everywhere. And the problem is there are functions whose integral is 0, right? Because the norm we're saying in L1 is the integral of f. So there's things that integrate to 0 that are not the 0 function. So this is false. This is false. This is false. And a good example to keep in mind is something like the function f of x equals 1 if x is exactly, let's say, 0 and 0 otherwise. So this is like some kind of function that has 0 everywhere and then it has a little hole and then it jumps up to the value 1. And when you integrate it, you get 0, right? Because the area sort of under 1 point is 0. In fact, in the last Tuesday problem session we did the integral. Last time we did the indicator 0, 1 open, and we saw that the integral of this was 1, and we saw that the integral of the closed 0, 1 is a step function, that's 1. And if you subtract these two functions, you will get this guy. So we kind of did this one actually already by hand, and that thing is a function. It's not the 0 function, because it's not equal to 0 everywhere, but it does integrate to 0. Okay, this kind of thing is called a null function. And you saw null sets briefly a while ago. And more generally, there is null functions. So here is definition. 2.6.2, a null function. And so these are functions with the norm of f equals 0, but f is not necessarily not the 0 function. The 0 function. Okay, so those are null functions. If it wasn't for null functions, then L1 would be a true Banach space. And there's a funny little way you can get around this by doing something called a quotient. Before we do that, let me prove one little theorem from the textbook again. This is theorem 2.6.3, and then we will do some quotient stuff. Theorem 2.6.3. If f is a null function, and g is another function with the absolute value of g of x is less than the absolute value of f of x for all x. So f is a null function. So remember, a null function you should think of looks something like this kind of function, right? It's like mostly 0, and then it has some non-zero parts, but the non-zero parts somehow are small enough that they integrate to 0. The non-zero parts are there, but they have area 0, right? Like a point or something like that. Okay, so this is saying f is a null function, and g is a different function, and it lives below f in absolute value. The conclusion is g is a null function too. Then g is a null function too. Okay, and the proof is kind of upsetting because the proof uses a weird hack about our system with the tilde equals. Okay, the proof, it uses a hack with the tilde equals definition. Okay, and here's the claim. Claim. G is equal to what? Remember, now we have the power. Earlier in the class, I was writing tilde equals and I said L1 or a step. From now on, I'm just going to write this, and it's going to be either one. So this is the way the textbook does it. We kind of needed the distinction when we had both of them, but now it really is that sort of like L1, E1. And so G is going to be a sequence of L1 functions that satisfy the conditions A and B as before. What sequence is it? It's very silly. It's f plus f plus f plus f plus dot 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 dot. Okay? So this is infinitely many f's. Add f infinitely many times. Now, if f was an ordinary function and you tried to add it to itself infinitely many times, this is like cuckoo bananas. Like, it doesn't make any sense. Like if f is the function y equals x, and you add y equals x to itself 100 times, and you get 100x, and then you add it to itself infinitely many times, it's just a function that's infinity everywhere. And this is like a nonsense function. But because f is a null function, actually this is okay. So let's check that this works. So check. And here in particular is where things would fail. So let's check. Condition A says the sum of the integrals from n equals 1 to infinity of the absolute values of the thing, they better add up to a finite number. Okay, so we're going to do the sum of all these infinitely many things. All the things are equal to f. So we're doing the infinite sum of the integral of f plus the integral of f plus the integral of f. Now, if f was any ordinary function, if you add something to itself infinitely many times, you get infinity, and then condition A would fail. But f is not any function. F is a null function, right? So f is a null function. F is one of these functions whose integral is 0. So because the integral of f is 0, this is the infinite sum of 0 plus 0 plus 0 plus 0. N equals 1 to infinity of 0, which is 0. 0 is the only number that you can add to itself infinitely many times and get something finite, which is why you can do this with null functions, this kind of trick of adding something to itself over and over again. Do not do it if it's not a null function. If it is a null function, then it's okay, and condition A works. Condition B says that g of x better equal the infinite sum of f of x, absolute value f of x, but not everywhere, when this infinite sum is finite. Is finite. That's what condition B says. Now here's the thing. Again, we're adding up this thing. What is the set where this is finite? So some people call this Z. I call it B for the bad set. B is the set of x values where n equals 1 to infinity of f of x is finite. Oh, no, this is the good set. Okay, G. It's crucial you have good set and bad set, because you're going to write if you give it a name like Z, you're like, which one is it? I don't know. G is the good set. When can you add up infinitely many values? So f of x is some value. You're going to add it up infinitely many times, and you're going to get that it's finite. Which values does that happen for? Yeah.
Whenever f of x is 0.
It all happens if and only if f is 0. If f is 0, you can add it up and it's a finite number. If f is any other number, then you add it up and it's infinity. So the good set is actually the same as the set where f of x equals 0. Right? That's the only way this can happen. The good set is where f of x equals 0. And g of x, I claim, equals this thing when f equals 0 because g is less than f. So since g of x is less than or equal to f of x, then g of x equals 0 also for any x in g. So if f of x is 0, then automatically g of x equals 0 as well. And then for any x in g, we have 0 is g of x equals the infinite sum of the f of x, which is also 0. So on the good set, it only happens when both things are 0, and then 0 does equal the infinite sum of 0. So it's kind of a very weird, normally you have to actually check that the infinite sum is like getting close to the thing, but in this case, either they're both 0, and then you're good, or if f is non-zero, then you don't need to worry about it. It's in the bad set, and it's like hands off. You don't check. Okay, so there you go. So that says that g is the infinite sum of the f's, and therefore, g is integrable. G is in L1, and the integral of g is less than or equal to the infinite sum of the f's, right? So normally it's less than the integral of all of the things in the list, but the things in the list are the same f over and over and over again. This is 0, and there you go. So g is a null function. G is a null function. Okay. This is a nice fact about null functions. The Thursday to Tuesday video is about almost everywhere convergence, which is more of this kind of shenanigan with the adding the same thing over and over again, and kind of these kinds of convergences, except for these stupid null functions and null sets and things like that. So this is something you kind of gotta get used to. Any questions or comments about that? Okay, in the last little 15 minutes here, I'm going to show you, remember L1 of R is not true. It's not a true Banach space because of null functions. Null functions. The way you can rescue this, and I'm going to tell you what it is here. We're not really going to use it in this course. So we're really going to do everything with this capital L1 of R the way we have been, and we're just going to keep in mind that, okay, sometimes if the norm is 0, you can be a non-zero function, but you're one of these silly null functions. But every now and then you need some proper thing, you need to rescue it. And so you rescue it, you construct a new space called L1 of R, where you write a script, a fancy L, okay? And L1 of R is a true Banach space, and it is equal to L1 except for null functions. So the way mathematicians would describe this is, okay, maybe I'll put equals in quotes. You put L1 of R, and you do what is called modulo out, quotient out, null functions. So you say like divided by. Normally people write it with a slash kind of this way. So you say L1 of R except for the null functions. And this is called a quotient or modulo. Okay, I will explain what this means. Who has heard of quotient or modulo before? Okay, most people. Very good. I'm going to start with a little warm-up example to tell you what this means, and then we'll do it for real, okay? Here is the example. Let's start with the natural numbers. So we're going to start with n, okay? N is the natural numbers. I'm going to start with 0. Sorry for people who like starting at 1. Okay, so 0, 1, 2, 3, blah, blah, blah. Okay. I'm going to make something, I'm going to define two numbers are equivalent. So n and m are equivalent if n minus m is a multiple of 2. A multiple of 2. Okay? So what this means is, and we're going to write it like this. N, we're going to write this, we're going to do 2. So if n is minus n is a multiple of 2, we write n squiggle 2m, and that means they're a multiple of 2. This thing is what is called an equivalence relation. An equivalence relation. And an equivalence relation means n should be equal to itself. So is n, not 2, n. Okay. Is n equal to itself? Well, n minus n is 0, and 0 is a multiple of 2. Because 0 times 2. Another one is, this is called reflexivity sometimes. Another one is like this. If n is equivalent to m, then m better be equivalent to n, right? So if a equals b, then b equals a. That better happen. If n minus m is a multiple of 2, well then m minus n is just whatever you multiplied by 2, do the negative of that. So this is sometimes called symmetry. And then last one is transitivity. So if m, n, and k are like this, so n is equivalent to m is equivalent to k, then n better be equivalent to k as well. This is sometimes called transitivity. And this is totally true if n minus m is a multiple of 2 and m minus k is a multiple of 2. Well, then I add those two multiples of 2 together, and then it's still a multiple of 2, and then n minus k will also be a multiple of 2. When you do this, so you have an equivalence relation, it will break up the space into equivalence classes. So all the numbers, 0, 1, 2, 3, and so on. Here, let's highlight them. 4, 5, 6. So we can highlight some more of them. They will be broken into equivalence classes. Sometimes you draw an equivalence class like this. So 0, this means all the numbers that are equivalent to 0. What numbers are equivalent to 0? Let's highlight them. So 0 is obviously equivalent to itself. 2 is also equivalent to 0, because 2 minus 0 is 2. 4 is equivalent to 0. 6 is equivalent to 0, and so on. So all those numbers are equivalent to 0. There are some numbers left over that are not equivalent to 0. In this case, those numbers are equivalent to 1. So 1 is some other thing. Let's draw that in pink. There'll be 1, and 3, and 5, and so on. Those are equivalent. And it turns out that everything in the natural numbers is either equivalent to 0 or it's equivalent to 1. So somehow 0 and 1 were the only equivalence classes we needed to make the natural numbers. This is the idea of a quotient. So the set of things, the set of equivalence classes, this is what when people say n modulo this equivalence relation, they say take all the things in n and break them up into groups of equivalence classes and think of the equivalence classes as a new thing. In our particular example, this is a set of two things, 0 and 1. Yeah, question over here.
This actually fails for symmetry though, because you don't have the negatives.
I don't think I need the negatives.
You do if you have a number
Oh!
larger.
Yeah, okay.
You need Z mod 2, not.
Okay, so we either need z, or we could just say we can measure if something is a multiple of 2, even if it's a negative number. So that's true. Yeah, would you be happy if I did z? We could do z. Let's do z.
It doesn't matter.
I wonder, yeah, I don't know. Maybe I run into something else. Okay, then we do dot. Yeah, I could have said the absolute value of the difference is a multiple of 2. Okay. But sure, let's make it z. I like z. Z is a cool one. And then, well, z is important because then nobody will get mad at me for including 0. This is the main thing. There's about half the mathematicians are like militantly angry if you put 0 in n, and the other half are militantly angry if you don't. So you're screwed either way. So this way we avoid those people. Okay. So the equivalence classes are 0 and 1. And when someone writes z mod this equivalence relationship, they're like, hey, I have 0 and 1. And I just think about those as their own thing. And the nice thing is you can do addition and subtraction on these. You can do, for example, 0 plus 0. That's kind of like, well, you have to kind of recognize what is 0. What is 0 kind of if you were gonna talk to someone on the street and you said, the equivalence class of Z modulo the symmetry relation division by 2, they'd be like, I don't know what you're talking about. But there's a special word for this thing. Yeah, do you know what the word is? Or maybe you have a question first.
Word for what?
The word for 0.
Aren't they just something numbers?
Even numbers, exactly, yeah. So normally we just say an even number plus an even number is an even number. And now it makes perfect sense, right? So as elements of Z modulo this equivalence relationship, any number that is in the equivalence class of 0 plus any number that is also in the equivalence class of 0 is still in the equivalence class of 0. So this is like a formal way of saying even and odd is to do this kind of thing. Some people call this a modulo because modular arithmetic is defined in this way. Okay, what is the point of all of this? Is we can do the same thing in our class. So we can take the space L1 of R, and we're going to define equal up to null sets. So two functions f and g are equal up to null sets means the absolute value of f minus g is a null set. Or, sorry, a null function. So a null function is something that integrates to 0. Okay, and then you have to check all the properties. Is f equivalent to itself up to null sets? Yes. The f minus f is 0. 0 is a null function. We're good. What about is symmetry? If f is equivalent to g, is g equivalent to f? And indeed, it's totally fine because it just depends on the absolute value of the difference. So if you swap them around, it's literally the same exact function. Okay, last but not least, what about f is equivalent to g and g is equivalent to h? Then can you say that f is equivalent to h?
Yes.
And the thing that we just proved, I think, will help you with that, but it's essentially you have this is a null function, this is a null function, and it'll be bounded. So f, it'll be yes by the previous lemma, since f minus h is less than f minus g plus g minus h. So if f minus g and g minus h are null functions, then f minus g is a function that is bounded by two null functions, and a sum of two null functions is a null function, and this is bounded by a null function, it's a null function. That was the lemma we proved, and that was why we needed the lemma. So the lemma makes sure that transitivity holds. The lemma, right? If you're less than a null function, you're a null function too. Okay, so finally, we have this thing, and so we can define this new space, fancy L1 of R, script L1 of R, which is L1 modulo equivalence up to null functions. What are the elements in L1 of R? If I'm like, hey, let me get something from L1 of R. They're equivalence classes of functions. So for example, the equivalence class of the 0 function, so if 0 is the 0 function, so it's the function, the 0 function, the equivalence class of 0 is all the null functions. All the null functions. Things that on their own are a null function, right? So there are things that are equivalent to the function 0. That's like if you put f equals 0, you would just get that g itself has to be a null function. You could also do things like, okay, what about the function y equals x? Let's call this L for line. No, wait, L is taken. Let's call it, let's just write x, and you'll know. X is the y equals x function. So this is, you could take the function y equals x, and you can add or subtract a null function to it. Okay, and this is a true Banach space. So this is null, y f of x equals x plus any null function. Okay. And this is a true Banach space. But the thing that's annoying about it, and the reason we don't use it, L1 is a true Banach space. Can anyone guess what is the super annoying thing about the space script L1 and the reason we don't like to use it? I will tell you the annoying thing. Because the elements are these weird equivalence classes, they kind of don't behave like functions anymore. So in particular, you can't evaluate at a point. What is, like if you say, what is this function, x at x equals 0.5? Any reasonable person would say, oh, that should be 0.5, right? Like if you want to evaluate this function at x equals 0.5, what would you get? You should get 0.5. That's the only sane thing. But you added and subtracted a null function, and so if the null function you added was exactly ruining 0.5, then you could get any value over here. So this could be anything. Anything. And this is so annoying that you want to not do this. So this is why. So no evaluation at points. At points. And so like, it's kind of just annoying to think about that. It's better for us to think about concrete functions. And then at the end of every theorem, we say something like, and the limit is 0 except for a null function. So the limit could be one of these like funny things with a little bit of stuff. Yeah.
So is that, I'll just use that same example, that X equivalence class, is that a function or a set of functions?
It's a set of functions. It's all the functions that are y equals x plus or minus a null function. Yeah.
Yeah, so when evaluating it at 0.5, that be evaluating every single one of them?
Yeah. So the point is that if every single function in that class agreed at 0.5, then that would be fine. But they don't agree, and they all have different values, and so there's no way to define it nicely. There's, for example, if you look at functions that are like continuous or something, then they all agree at like a point because like you can fix the holes and stuff. So you can like do nicer things. If the functions are continuous or like mostly continuous or something, then things are better. But yeah, so this is why we don't use script L1. We just use regular L1. And the Thursday to Tuesday video is all about this almost everywhere convergence, which is like convergence except for these stupid null sets and stupid null functions. Okay. All right, I think we're a little over time, so thank you for waiting. And I'll be here for a few minutes if you have questions. But otherwise, see you guys on Tuesday for our first problem session since the break. Yes.